is going to be solving exponential equations which we've already done before, right? We've already solved exponential equations. We were using the little charts. Okay, and do I need to take that phone? All right. So we've done solving exponential equations. We use the little charts. So today we're going to solve exponential equations, but we're not going to use the little charts because we're going to look at specific problems where the charts would not work. So today we're going to solve exponential equations and we're going to use logs. Using logs, because logs are the inverses of exponential form. So we're going to solve exponential equations using logs. And I shouldn't see any earbuds. Thank you. All right. So first example. Okay, so if I have 11 to the v power equals 90, 11 to the v power equals 90, I have an exponent of v. I want to get the v alone. I want to get rid of the base of 11. How could I get rid of a base of 11? I'm going to log base 11 both sides. So log base 11 the left side, because that's going to get rid of it. Log base 11 the right side, because whatever I do to one side of an equation, I have to do to the other side. So I'm going to say on the left side, those two bases, log base 11 and then exponential of base 11, those are inverses of each other. They cancel each other out. And so I just get v. The v is isolated now. On the right side, I get log base 11 of 90. Now, if I wanted my answer in exact form, this is it. This is kind of like having a fraction answer. This is exact form. It's perfect. I didn't round anything. This is kind of like having a square root answer too. So this is the perfect answer. If I want to have the approximate answer, then I'll plug it in my calculator and see what the decimals are. So let's go ahead and plug this in. How do I type log base 11? Math, up, log base 11 of 90, and then what do I get? 1.877. So V is approximately 1.877. Okay. Example 2. All right. So they're not always going to be that simple. Let's make it have more steps. So we're going to say 3 times 12 to the negative 4k. I'm giving you a lot more steps this time. Bring it on. That was a challenge. Minus 2 equals 72.5. Okay. So we're just going to remember that whenever we're solving an equation for a variable, we just have to do PEMDAS backwards. So the first thing I do is I ask myself, is there anything easy to add or subtract to move it away from the variable? Add the 2. The 2 would be easy to add or subtract to get it away from the side with the k. So add the 2. That leaves me with 3 times 12 to the negative 4k equals, now I've got 74.5. Okay. When I'm doing order of operations backwards, what's my next step? Yeah, multiply or divide. Is there anything that I could multiply or divide over to the other side? The 3. I've got a 3 in front. That's kind of like a stretch, right? If we were to be graphing this, this would be like a stretch. So I'm going to divide by 3. Divide by 3. I'm guessing that's not going to divide. Yeah, it's like a decimal that keeps going. Okay, so I'm just going to leave it like that, even though it's a decimal within a fraction, which we know is usually a no-no. But in this case, it's going to keep us from having to write a decimal that, like, we don't want to round in the middle of a problem, right? So I'm gonna keep writing this as a fraction because right now I am avoiding rounding in the middle of a problem. So I'm gonna leave it like this. Okay, what's the next step in order of operations backwards? What's the next step? Add, subtract, then multiply or divide, then before parentheses, exponents. So next we have to say, is there like an exponent I should introduce, an exponent I could get rid of? I'm dealing with the exponent. So here the exponent is what I'm actually trying to get to. So I need to get rid of the base so that I can get to the exponent. So the base of 12 is what I have to get rid of. And so I'm going to log base 12 each side. I'm going to log base 12 each side because I want to get to the exponent. That was my next step. I'm trying to get rid of the base so I can get to the exponent. Okay, so negative 4k. Now the P is for parentheses. That's the grouping symbols. That's kind of like the inside of the function. It's whatever was trapped inside. We know that in exponential functions, the x minus h part is the exponent. That's the inside of the function. So what we did, even though it wasn't in parentheses, is we just got to the inside of the function. It just happened to not have p with it. It happened to not have parentheses with it. Okay, but we did just get inside. So this equals log base 12 of this fraction, 74.5 over 3. Okay, and then what we do is we go back to the beginning because now we're taking the inside of the function and we're just doing whatever we can to get that variable alone. So what do you have to do to get the variable alone? Divide by negative 4. It looks crazy, doesn't it?
It looks ugly.
Yeah. We are going to plug just the whole thing in the calculator, and it's not going to be that bad. Yeah.
Why did you put E for 3? Isn't E the 2.718?
This isn't Euler's number. This is PEMDAS backwards. So please excuse my dear Aunt Sally. So we were just doing that backwards. Yeah. Okay. So this is a fraction. How do I get a fraction on my calculator? Alpha y equals, okay, I got negative 4 on the bottom, okay. How do I type in log base 12? Math, up, okay, log base 12, and then 74.5 divided by 3. You can type it in like a fraction or you can type it in like a division problem. Both of those will work. So I typed it in like a division problem, 74.5 divided by 3. So you can type it in that way, or you can in here do alpha y equals and do 74.5 over 3. Type it in like a fraction. That would work as well. Okay. And we're going to get some sort of weird decimal. Negative 0.323. Is that what you guys got? Yeah. Yep. So this, we would say, is the exact answer. I know it has a decimal in it, but it's not a decimal that's been rounded, which is why it's an exact answer. So this is the exact answer, and then the approximate answer is negative 0.323. Now, we could have used decimals as we went, as long as we left them in the calculator and didn't write them on our paper and then use a rounded version. So if you wanted to do like 74.5 divided by 3 and write 24.83 and write the 24.83 on your paper, that would be fine. You just have to keep that decimal in your calculator and keep using that decimal as you go, and not use a rounded decimal on your paper in the middle of the problem. Okay? Because in math, the further advanced math we go, the more they expect you to have perfect answers. So we don't round in the middle of a problem, we round at the end of the problem. Does that make sense? Okay. Not 15, you don't write decimal places at all, not till the end. So if you're going to use a decimal, you have to leave it in your calculator so you're using the perfect decimal the whole time. Does that make sense? So just leave it here. So if we were using it, we'd say, okay, this is what I was using. Then I needed to log 12 of that. So I could do math up, log base 12 of this. Oop, I put that in the base. 12. And then right here of that, and I plugged it in. I just went up and I highlighted it and grabbed it. I went up, press the up arrow and just press enter. So you just have to keep going up and grabbing that answer so that you're like copy pasting it. And as long as you're copy pasting it, you're fine. But if you round that number, if you write 24.8 on your page and then you use 24.8, you can't trust your final answer. Your final answer would be wrong. So if we had that and then divide that by -4, then we get the same answer. But if you did math up, log base 12, 24.8, and then divided that by -4, you might have a similar answer, but the rest of your decimals would be wrong. So it depends. Some problems it wouldn't make a difference, some problems it would, but overall they say don't round until the very end. Okay, and in some problems it could make you off, make your answer off by like hundreds of thousands of digits just because you rounded too early. Yeah. Okay, let's try another example because that one got real funky. Example 3. I'm gonna throw an E at you guys. Are you guys ready for an E? Did you say this shit? Yeah. I can hear you. I can hear you. I mean, I'm a teacher still though. You gotta like filter it. I'm a delicate soul. I wear flower dresses. Man. All right. I appreciate it. All right, first step. Is there something we should add or subtract to get away from the other side? Wiggly means that I rounded. So this is the perfect, equal is a perfect answer. Wiggly means I rounded. As soon as I cut off numbers, I got to say approximate. Because I didn't write the whole answer down, I cut off numbers. It was way more than 3 decimals. It was a bunch more. So as soon as I cut off some, then I got to say this is approximate. Yeah. All right. So here, what's the first thing I can do? I got to add or subtract something over to the other side. Okay. Plus 7. So we've got 2.8 times e to the a plus 6 equals 11. Okay? What's my next step? Multiply or divide, and we're going to divide by what? 2.8. Does 11 divide by 2.8 nicely?
No, it divides meanly.
It divides meanly?
Yes.
Oh, yeah, that's not good. Okay, so we're going to leave it as 11 over 2.8.
Now, to get rid of that e, we got to use the base of 2.718, right?
So we are going to log base e on both sides, which is, I'm going to go ahead and just write log base e, because we're getting rid of the base, right? This is our step. We're trying to get to the exponent, log base e. So I'm going to go ahead and cancel this. And these are my notes, so I'm actually going to write this step down because I don't want to forget what I'm doing. And then somebody remind me, what is log base E? It's the natural log, which is ln. Log base E is ln. Yeah, this is ln. Okay, so we have a plus 6 equals ln of 11 over 2.8. Okay? So some students, anytime they see the E, they go, oh, I just have to ln that. That's how it gets rid of it. And some students have a hard time seeing that. They don't think of E and ln as being opposites. You E. You E it. So some students, the connection between the E and the ln just makes sense. And some students, whenever they see an ln, they have to remember, oh, ln is just log base E. So some of you guys will be able to go directly there. Some of you guys will have to stop and remember every single time you see an ln, oh yeah, ln is log base E. So if you didn't go to the ln connection right away, that's okay. Just remember, ln and log base E are the same thing. Ln and log base E are the same thing. Okay, so we have a plus 6 is ln of 11 over 2.8. So at this point, we got into the inside of the exponential function, right? We got into the exponent. And so now we got to go back up to the beginning. And we're going to get the variable alone. We're just going to subtract 6. It is happening after all this stuff did. So the subtract 6 is just on the end. So the exact answer for A is ln of 11 over 2.8 minus 6. And now we're going to type that into our calculators, see what that is. Ln of 11 over 2.8 minus 6. What do you guys get? Negative 4.632. So you guys don't have to put the squiggly equals, but when you see me put it, I always put the squiggly equal sign because I rounded the number. Anytime I've written a decimal and it's not the perfect decimal, it's not the whole thing, I cut some numbers off. If I cut the numbers off, you're going to see me put a squiggly equal sign. And that shows the person looking at my paper, oh, that decimal is not what she saw on the calculator. She cut those numbers off. Okay? 1 second. Okay. Do you guys want to see another example, or do you think you're ready to try some? Ready to try? Okay. I'm going to go grab the copies. And we have a coloring sheet. So if we look at number 1, is number 1 a problem where you would change the base and use the chart? Or are you going to have to take logs of both sides? Number 1 is the chart. For number 2... Yeah, and you actually don't even need the chart. Why don't you need the chart for number 2? The bases are already the same. Okay. For number 3, can you use the chart on number 3? No. The 8 looks like maybe you could use the chart, but the 53 tells you you definitely cannot use the chart. So on number 3, you're going to have to use logs. Okay. On number 4, can you use the chart? No. Number 4 is definitely logs. Okay? Number 5. 216, 216, 36. Chart or logs? Chart. Number 6. No chart or log. You got 2 bases of 5. Just cancel them out. Okay. Yeah. Okay, number 7. Chart or logs? Logs. Okay. Number 8. Chart or logs? Log. Okay. Number 9. Chart or log? Chart. Number 9. Number 10. Chart, or it's a chart, it's just not on your chart. Oh, it's not going to be hard. Yeah. What are you going to use for the bases of number 10? 10, base of 10. Oh my gosh, you guys. Do you recognize number 11?
Yeah.
Why did I do that?
To help us out. Thank you. Oh no, you're not gonna let us do it.
Oh. I mean, you can do it if you want.
Are you gonna count it if we do it?
Sure. Here, Gigi. All right, number 12. Is that a chart or should we use logs? Log. Number 13. Chart or logs? Chart. Okay, 14. Chart or logs? Chart. Okay, 15. Chart or logs? Logs. Okay, 16. Chart or logs? Logs. Okay, so can somebody kind of summarize what's our clue that we're going to use a chart? Yeah, it's like recognition of those numbers, maybe. So it has like those base numbers. You're going to see numbers like 32, 64, a lot more even numbers for sure. Okay. What's maybe a clue that you're probably going to need to take logs?
You have like a number like a 7 and an 8.
7 and an 8. Mm-hmm. Another thing that I've noticed that you're going to see if you're going to take logs is if it's got a plus in the problem. Mm-hmm. Or like a minus in the problem. That's going to make it so you have to take logs. Because logs has it where you can do order of operations to kind of isolate it. And the chart problems don't really have that. They have it in the exponent, but they don't have it otherwise. So that's a big difference. Okay.